Hi everyone, this is a lecture about deriving the logistic growth equation. So just to recap, density dependence means that the intrinsic rate of growth decreases as resources get used up and as the population size increases. So what we're going to do is we're going to start with the basic idea of exponential growth. So let's write our exponential growth equation in continuous time. And let's introduce a new idea, which is that the intrinsic rate of growth depends on the amount of food that's available. So over here, I'm going to write R is equal to BF. And F is the amount of food available. And B is how much intrinsic growth you get per unit of food. So this number B, it might be different for different populations. For an insect population, it might not take very much food to generate a large amount of reproduction and increase in survivorship. For an elephant population, it might require lots and lots of food. So that's what this B is here. It's a bit confusing maybe because it's called B and you think births, but it's really an intrinsic rate of growth, so it's births minus deaths like we saw for the exponential equation. So now we want to introduce the idea that intrinsic rate of growth depends on food into our exponential equation. So let's just make the substitution for R. And the left-hand side here is just the same as it was, the rate of change in the population size with respect to T. So I'll write it over here just so we don't forget. N is your population size. So far what we've said is that the intrinsic rate of growth depends on food. We haven't said anything about how the amount of food changes with population size. So let's write another equation, and let's say that the total amount of food is equal to the amount of food that's available and the amount of food that got used by individuals. So here F is the amount of food available. I actually wrote that out there already. So F of T is the total food or total resources. And C is the amount of food that gets used per individual. Okay, so let's think about what the difference between B and C are. So B is the amount of intrinsic growth that's generated per unit food, whereas C is the amount of food that's used per individual. So what's the difference? Well, not all of the food or all of the resource is going to get used for survivorship or reproduction. Some of it's going to go into metabolic processes as well. So that's C is the amount of food that's used by each individual, not just for reproduction, which is what B is. Okay, so now we have an expression that includes the amount of food that's available for new reproduction. And we can rewrite that by subtracting Cn from both sides. So now we get f of t minus Cn is equal to F. This is our expression for the amount of food as it depends on population size. So we see that the amount of food available decreases linearly with the number of individuals in the population. So let's make a substitution for F for our expression of how F changes with population size. So we get the intrinsic growth rate per amount of food, and then that the amount of food available is equal to the total amount of food minus the amount of food that got used by individuals in the population multiplied by the population size. So that's just everything there is F, and this equation and this equation are exactly the same. It's just that we've made this substitution now for how food changes as a function of population size. Okay, now I want to just rewrite this a little bit. So what I'm going to do is divide everything in the bracket by f of t and multiply the outside by f of t. So I'm multiplying by f of t and dividing by f of t, so I'm multiplying by 1. So let me just check that that is what I want to do here. Yeah. Okay, so I'm going to multiply by f of t, and I'll just bring this n across. So that's the multiplying by f of t part, and now this is the dividing by f of t part. So f of t divided by f of t is 1, and then we have c divided by f of t times n. And now we're going to define a little bit of new notation. So we want to define the carrying capacity, so the maximum number of individuals that can be supported by the resources. And we're going to define K equal to f of t divided by c. So over here, K, carrying capacity, and I also want to define R tilde is equal to B f of t, and R tilde is the intrinsic growth rate at low population size. So let's make those substitutions. So this here is R tilde, and this here is 1 over K, and so we're going to get R tilde n 1 minus n over K. That's our expression for the change in population size per unit time when the per capita growth rate depends on the amount of food, and the amount of food decreases linearly with population size. So this is our logistic growth equation, and in your book they rewrite it slightly, so they just multiply, just write this as a common denominator, this part in the bracket. So they, in the book they write dn dt is equal to r n, and then it's k minus n divided by k. So that's just putting everything that's in the bracket under a common denominator, and also it's just a change of notation. So we let r equal R tilde. And so these are the same, just slightly rewritten. growth equations in continuous time. Now, one thing that you should notice is that what R is in the exponential equation and what R is in the logistic equation is slightly different. So in the exponential equation, the intrinsic growth rate doesn't change. So, I don't know, there's no relationship with density, right? For the logistic growth equation, the intrinsic growth rate changes with density. And so the intrinsic growth rate is really the intrinsic growth rate at low density. This R is the intrinsic growth rate when all the resources are available. You have the total amount of resources to exploit. So R in this equation is the intrinsic growth rate at low density.